if so M of one-dimensional algebra, and suppose the pre-dual is separable. Okay, so what does this mean? So it is separable. Separable means as a Banach space, it's separable. Any subset of a matrix, separable matrix space is separable, right? And so, in particular, the unit bond of M star is separable, right? The unit bond is separable. And so suppose rho and phi n is dense in the unit bond. Okay, so what I want to say is that the unit bond of M is sigma weakly separable but the unit bond, the sigma weak topology is compact, right? So if you have a compact Hausdorff space which is separable, that means it is metrizable. Right? All good things happen for compact spaces which are separable. Okay, so and in fact, okay. In fact, I will explicitly exhibit a metric for you. Right? So proof. So define dxy. These xy come from the unit bond of M. Okay. Yeah. So I want to say that D defines the sigma weak topology on the unit bond of M. So I want to say that, huh? Function is an element of M lower star. So M lower star can be thought of as sitting inside M upper star also. This is the M lower star double star. This is the usual embedding of Banach space into second dual. That is, I can think of elements of M as linear functions on M lower star, Or I can think of elements of M lower star also linear functions on M. These are those linear functions on M which are sigma weakly continuous. So think of phi n as functionals on M. Okay, so I want to say that xi converges to x sigma weakly if and only if d of xi x goes to 0. This is a priori, it's a net. But this is because, okay, so let me, huh? Weak star topology. There is sigma weak topology, which is a weak star topology, which is against things in M lower star. Right? So this means, of course, that phi n of xi converges to phi n x for all n. Right? So there are two implications you must prove. So this way, it is clear that phi n of xi minus x goes to 0 for all n. There is the limit I phi n of xi minus x is 0. Because xi is a net converging to x. Okay, so suppose epsilon is positive. Let us show that xi converges to x in this metric. So first I can choose pick n, so just then summation n plus 1 to infinity of 2 to the minus n. See, this is bounded by 2. Phi in the unit ball and x is also unit, x and y are unit vectors. So this is bounded by 2, so this is bounded by 2 times 2 to the minus n. Right? So this is essentially 2 to the minus n, or plus or minus 1. And so this is, I'll probably need this later. So what is this thing? What is summation r power n equals n plus 1 to infinity, where r is less than 1. So let's pull out an r power n plus 1, and then it is the geometric series. So it is this times 1 over 1 minus r. Right? Okay, so this is how much? This is equal to half times 1 by 2 to the n plus 1 to 1 over 1 minus half. Huh? So, how? 2 times. This 2 and this cancel out. So this is just 1 by 2 to the n plus 1. So this is 1 over 2 to the n, 1 over 2 to the n. N minus 1. 1 over 2 to the n minus 1. Anyway, so I choose a large n, so this is smaller than epsilon by 2. And then I have to look at all the first n terms. I know the phi n of xi minus x goes to 0. So I can choose for each n, I can choose I1 up to In such that pick the existing indices I1, In such that for all I bigger than or equal to In, Ij, mod phi j, no, phi j of xi minus x is less than epsilon by 2n. You can do this. And now, because the directed set, so you choose an I which is bigger than all of them. There exists such an I. Let me call it I naught. And then what we see is that I bigger than or equal to I naught implies the sum of the first n terms will be smaller than epsilon by 2. The sum of the tail will be smaller than epsilon by 2 by choice. So it's going to be smaller than epsilon. Conversely, what does it mean to say that d of xix goes to 0?
So this gains phi nx I converted to phi xi.
So dxix goes to 0 certainly implies that phi n xi goes to xi minus x goes to phi nx for all n. That is, if you put this metric topology on the unit ball, on the unit ball of M, every phi n is continuous. But then if you take any phi in M lower star, the unit ball, it is a norm limit of phi n's. But the phi n's converge to phi uniformly on the unit ball of M. If all the phi n's are continuous, then phi must also be continuous. So this means that phi xi converges to phi x for all phi n M lower star. And so for all phi in M lower star. Scaling doesn't change anything. That is xi converges to x sigma weekly. So we've shown that the unit ball of M is a compact metrizable space in the sigma weak topology. Okay, now what do I want to do with this? Okay, then I'm going to use the kind of thing that we did long ago. If you take a representation of, the unit ball of M can be thought of as some compact metric space. There is in the with respect to this matrix, I can view this as a compact metric space. Right? So that I take this unit ball and so this is mumbling around. So no, as you see, I didn't complete figuring out the proof of this. See, basically what I'm trying to say is that because of this, the Borel sigma algebra is going to be countably generated. No, but I don't know. I need a representation of. Why am I going through all this? Why don't I just take the. So the no. So let me go. So this is so separable. Right, in the weak star sigma weak topology. So let Xn be sigma weakly dense in the unit ball of M. And I'll further break it down and take the Cartesian decomposition. So what I'm trying to say is that it follows that therefore M1, therefore M equals the Neumann algebra generated by Xn, where Xn is a family of self-adjoint. By taking the Cartesian decomposition, I can conclude that any von Neumann algebra with separable pre-dual is generated as a von Neumann algebra by countably many self-adjoint elements. Okay. From this I want to go to function spaces. So what do I do? Xn. See, I'm handicapped by the fact that I didn't do Gelfand theory for C-star algebras here. There is this. So I should have done this, but I never got around to do it. So which is that if A is a commutative separable C-star algebra, separable unital, if and only if A is isomorphic as a C-star algebra to C of sigma for some compact metrizable space. So this is what is true of any commutative C-star algebra. Okay, so what do I want to do? I want to take okay, over there what we had was that M was W-star algebra generated by a sequence Xn. Right? The assumption that M had separable p-dual implies that M is the one-dimensional algebra generated by a sequence of self-adjoints. Right? So I want to now go to the von Neumann version of this statement. So suppose, I want to say if M is, suppose M is a commutative von Neumann algebra with separable p-dual. Okay, then I want to do the following thing. So I want to prove this following theorem. Then M is isomorphic to L infinity sigma mu, where this is compact metric and there is a probability measure. And of course with respect to the Borel sigma algebra of sigma. So I want to say that all commutative von Neumann algebras look like L infinity. Okay, now the way I'm going to, I hope to do this is to say the following thing. So now I take A to be, let A, no. A equal to C star of all the xn's. Then A is a commutative C star algebra and it is separable because why? If you take finitely many, if you take words in xn and xn star and take, there are only countably many of them, and take rational linear combinations of those, meaning complex rational, that will give you a dense subspace of this C star algebra. So this is a separable commutative C star algebra. So by invoking the fact for C star algebras, we conclude that this is isomorphic to C of sigma for some compact metric space. And so what do we do with that? But I still See, if I knew that M was sitting inside a B of H, then I can use some tricks I've used this in our proof of spectral theorem. Namely, I have a representation of C sigma. Because A is sitting inside M, A generates M as a one-Neumann algebra, and M is sitting inside B of H. So we have this isomorphism from C sigma to A will give us a representation of C sigma on Hilbert space. But then that, because of separability and so on, you can write that representation as a direct sum of cyclic representations. Each such cyclic representation will look like a pi mu for some measure mu. So this representation can be thought of as direct sum pi mu n, where I can assume the mu n's are probability measures. And then I will take mu to be summation 2 to the minus n mu n or something. Then I will have a probability measure, and one can show that you have actually the representation extends to a representation of L infinity sigma mu on the whole Hilbert space, such that the image of image of C sigma is A. That is the initial representation onto C sigma. C sigma acted as multiplication operators, and the direct sum of those multiplication operators is what this A is. By definition, A is the image of pi. And so it will follow that there is that argument okay, so let me, I'm verbalizing too much, I was right. See, let pi, but I don't know that M is sitting inside a B of H. So for that I'll have to use, if I want to go that route, I must show that any such, so there is that theorem also, that any one-Neumann algebra with separable pre-dual admits a faithful normal representation on separable Hilbert space. So I'll have to go to that, which requires some Sakai's theorem, that requires an understanding of a normal linear functionals on one-Neumann algebras, which we haven't gone into. So let me try and ad-lib my way through this thing. So what I do is the following thing. Is no, so I don't want to say this. So what I want to say is so what we know is that M is the one-Neumann algebra generated by sequence of self-adjoints. Right? So then I write B for set of all where U is an open interval with rational endpoints of this form. Let me say Rs with Rs in Q. Just take all possible rational intervals so that I have a countable collection of open intervals which generate the entire sigma algebra. Right? So then I want to say, let me write En, and then I look at the collection of all indicator U of Xn. I take all spectral projections of each of these self-adjoints which correspond to such rational intervals. Then what I have is, after all, it is some countable family of projections. And all the xn's were from M, and the xn's generated all of M. Now, so I want to say that because the xn generate all of M, if I take W star of, so I'm just trying to say that I can choose that family of self-adjoints as projections. Because we have all rational indicator functions of spectral projections of Xn, then I will have all spectral projections of Xn. So I will have all the Xn's I will have, and hence I must have, if I have all the Xn's, I must have M, the generate one M. So the point is that M is generated by a countable family of projections. Okay. So now I want, from this I want to get this see, and this is a family of commuting projections. See, if you have a bunch of commuting projections, that is really like having a bunch of sets. If you have commuting projections, they would look like indicator functions of sets. And if you believe the theorem, then of course it is true. If you know that M is going to look like an L infinity, then the projections in M are going to be indicator functions. And so here all these EMs are going to be indicator functions. And so this is how I want to try and set up this proof, but I still need to get this measure. How do I get this? How do I get the measure? Oh, I do have a I do have a measure. Namely, see if I take okay, so going back to the thing, M had separable pre-dual. So there was that sequence phi n which were in the for me to get positivity again I'll have to use Sakai's theorem. And this is what I should have done. See the fact is this is trying out to be a disaster. I wonder, increasing family of okay, so to try to salvage the thing, so let me assume that part and then prove. There is, rather than assuming that, let me prove the modified version of this theorem. I say that if M contained in B of H, where H is separable, and if M is a commutative one of an algebra, then I want to say that M is isomorphic to L infinity sigma B mu. For some compact space and for L sigma algebra and probability measure. Okay, so what do I want to do? I do this. Okay, then now I'll call this B. Let B be the C-star algebra generated by all these ENs. Sorry?
That in isomorphic to L infinity, assuming that it has pre-duals.
Assuming it has?
M has separable pre-dual. That is the definition of permanent algebra.
No, I'm assuming
BH.
that M is sitting inside B of H and where H is separable. That will automatically mean that M has separable pre-dual. Okay, so what is going on? We know that this is going to be isomorphic to some C sigma. Actually, for this, I need even have chosen these ENs. I could have stayed with my XNs that I had before. Okay, so what? Let me call this mapping. So we have the mapping pi from B to B of H, which is this isomorphism. Going backwards. From C sigma, damn, I'm saying all the wrong things. See, C sigma was isomorphic to a So what did I do? I just took the separability hypothesis in whatever form, guaranteed that M was actually generated by A, where A is a separable C-star algebra. I called it generated by Xn or En or whatever. So, and suppose M is commutative. That implies, of course, that A is commutative. Implies by that Gelfand theory that A is going to be isomorphic to C sigma for some compact Hausdorff sigma. That means, so I'm assuming that now that M is contained in B of H. But that means I have a mapping pi from C sigma to A, which is this isomorphism, which is contained in B of H. So I have a representation of C sigma. So I'll recall the steps very quickly of the spectral theorem, what we did. So what we did was to say that you first take any vector xi in H and look at A xi. This is an example of a cyclic, this is a cyclic subspace. So what I'm saying is, see, everything in A looks like pi of something, right? So then one said, you consider the functional phi from A to C defined by phi of f equal to pi f psi psi. And one observes that this gives a positive functional on A. Not A, I should say from C sigma, sorry. Look at the mapping from C sigma to the scalars defined by phi of f is pi f psi psi. Then this is, if f is positive, then this is positive, and there is a positive linear functional on C sigma. And the Rees representation theorem says that every such representation comes by integration against some measure mu. So what does that say? They say that this is equal to integral over sigma f d some mu which depends on psi. And then what one observes is that if you look at the collection of all f where f is, I'll call it a fat. By f hat I mean f hat equals f thought of as an element of L2 sigma. Then look at all these things. Because continuous functions are dense in L2, L2 is the completion of continuous functions by Lusin's theorem or whatever. So this is a dense subspace of L2 sigma. And the set of all pi f sigma, pi f psi, this is a total space in things like this are dense in this space. Things of the form pi of psi constitute dense subspace of this subspace, this cyclic subspace for this for A. So, and one observed that this association from f hat to pi of psi see here is the dense subspace of L2 mu. Here is the dense subspace of A psi, which are both indexed by C sigma. And this is an inner product preserving bijection. If you take f hat g hat, that will be exactly pi of psi inner product pi g psi. So there exists unitary representation U from A psi to L2 sigma mu such that U of pi of psi equal to f hat for all f in C sigma. And the thing that one should observe about this mapping, that not only see what we're using, if you restrict pi f to the cyclic subspace, if we call pi f restricted to xi as pi sub mu xi of f. The pi sub mu represents C sigma on L2 sigma, where continuous functions act as multiplication operators on L2, and they are bounded operators there. But the point is that once you've given yourself a measure on sigma, that multiplication representation makes sense not only for continuous functions, but for things in L infinity. So this extends to a representation of L infinity sigma mu xi on this space in such a way that it is appropriately continuous. It satisfies bounded convergence. Right? Let me say, I'll loosely call it SOT continuous representation, by which I mean if Fn converges to F almost everywhere, mu xi almost everywhere, then pi Fn will converge to pi F SOT for this representation. Wherever you have one measure mu, you can do this thing. And then you turn around and say, by appearing to Zorn's lemma or whatever, you can write H as a direct sum of cyclic representations. You can just exhaust the thing by a direct sum of cyclic subspaces. Each of those cyclic subspaces, if you take the representation of C sigma, restrict to that, will give you a measure mu xi n or mu n. So this will give rise to measures, probability measures mu n. So I should have said, if see, this mu xi will be a probability measure if xi is a unit vector. See, I didn't do that verification. See, the thing you had to verify was that pi mu f xi inner product pi mu g xi mu xi. Because pi mu is a representation, this is the same as pi mu of g bar f xi xi. This will come out here as adjoint, and pi mu g star is pi mu g bar. And so this is equal to integral of g bar f d mu. which is in a product of f hat and g hat. This was the verification you had to do to prove the existence of the unitary operator. That unitary operator is going to send pi mu of psi to f hat. If we take f to be the constant function 1, that unitary will send psi to the constant function 1. Now that will be a unit vector in L. If this psi was a unit vector, because u was unitary, 1 hat must be a unit vector, which is a statement that mu is a probability measure. Right? So you can, these cyclic subspaces, cyclic vectors, you can always assume are unit vectors. So you exhaust H as the direct sum of cyclic subspaces generated by unit vectors to be able to say that pi is unitarily equivalent to a measure of the form pi mu, a representation of the form pi mu n, direct sum pi mu n. And then what one is saying here is that if you take what do I want to say? If I define the new measure mu by summation 2 to the minus n mu n, then see what I'm saying, mu e is 0 if and only if mu n e is 0 for all n. But if you look at the multiplication representation of L infinity of something or something else, so if we take such an E, okay, L infinity mu is an equivalence class of bounded functions and so on, but you just think of that as it extends to a representation of bounded measurable functions. So the norm is the L infinity norm. The image under the representation of a bounded measurable function is the L infinity norm of that bounded function. That is what that extension theorem stated. Now I'm saying you take any bounded measurable function, and what this will say is that bounded measurable thing will act on each summand as a multiplication operator, and hence as a direct sum. And so we see that pi mu, I shouldn't say pi mu, f going to direct sum pi mu n f will make sense, and it will define a representation, an isometric star algebra representation of L infinity mu into B of H. And the image of the representation will be closed under this the SOT. Like if you have things which converge almost everywhere here, so the point is that this gives a representation of this one-Neumann algebra, an isometric representation into B of H, so its image is going to be a one-Neumann algebra. So we proved the thing that the image of, under any phase,
Sigma is continuous.
but
The star representation is the image of a star representation is one-Neumann algebra. If you have a M1 to M2 and there is a star isomorphism.
Sigma is continuous. This is not a star isomorphism. This is into.
This is the
no. It will be onto its image, no?
On to its image one. Image will be one.
But I'm saying the image will be closed under strong SOT convergence of sequences.
Isometric. Isometric also.
Yeah, this is isometric. Which extends to an SOT thing. See, the point is that if I call this representation pi tilde, I have a representation pi tilde of L infinity with the property that whenever a sequence we have a sequence converging in the sense of bounded convergence. If you have a sequence uniformly non-bounded which converges almost everywhere, then the image converges in SOT. That will show that the image of the representation is closed under limits of uniformly bounded sequences, SOT limits of uniformly bounded sequences. By Kaplansky density theorem, that is enough to say that the image is actually a one-Neumann algebra. So, okay, I'm not doing this, I'm not doing a good job, I realize, but the point is that the image of this representation will be a one-Neumann algebra and it contains that image of C sigma, which was by definition that A. And M was the one-Neumann algebra generated by A. So this would have shown in this convoluted fashion that M is isomorphic to L infinity sigma mu to this L infinity sigma mu. Okay, I'm sorry I made a complete hash of this, but I hope you at least got some idea of the proof. There are lots of things to.
So assuming that M is subset of BH, you are putting that M is equivalent to L, not that separable principal.
That is right. That is right. But to complete that proof, I need to show that if a separable pre-dual, then there exists a faithful normal state. And hence that I can do GNS and get a faithful representation on a Hilbert space. And the separable pre-dual will imply that the image will be, the Hilbert space will be separable. Because there is a cyclic vector, and if you take a countable dense sequence in the sigmoid or topology or whatever, then if you look at pi fn acting on xi, where xi is that cyclic, that one hat, then that will be, if you take its weak closure, because Fn was weakly dense in M, that will be a weakly closed subspace of Hilbert space, and hence strongly closed, and so that will have to be the whole Hilbert space. Sorry, this was very, very confused and unsatisfactory conclusion to a course of lectures, but actually I had wanted to do cross products, because we'd started doing the group algebra, group one algebra. I wanted to give further examples of this thing, and because when I did in the lecture on group one algebras, I said that something is a trace, that it is a finite one another, that identity, the f going to lambda f one hat, that you are actually in the JNS space for a faithful normal tracial state on that one algebra, and with the JNS vector being one hat. So unfortunately too many technicalities one will go through. See the point. See the GNS representation. So I've been saying if you take a faithful normal state, you can take the GNS representation. And so what is so good about this thing? Then it turns out that this GNS representation for any faithful normal state, those two representations will be unitarily equivalent. That will translate to the fact that if you take any automorphism of the one-Neumann algebra, that will be implemented by a unitary in the operator, in the Hilbert space. So when a one-Neumann algebra looks like it is in the, so you say it is in the one-Neumann algebra is in standard form if it is being seen as acting in the GNS space. That is the group one-Neumann algebra LG that I wrote down is in standard form, because I defined it for you as a subspace of L2G acting on L2G with those generators acting with those translations. And so when a one-Neumann algebra has a cyclic and separating vector, you say that it is in standard form. And whenever you have any two things in standard form, then there's unitary which intertwines between those Hilbert spaces, which maps this one-Neumann algebra action onto that. So the standard form is somehow canonical, and it is naturally identified with the but there's just too much to say in this subject.